Swayam Prabha. Digital India. Educated India.
In the last class, we were talking about subjective, objective evaluation. We run it a bit fast because we wanted to get an overall picture. We didn't go into details of some of the things which may be of interest. You may be wondering, for example, what are the type of questions that are asked to expert driver, and what is he supposed to know and answer? How does he answer? All these things, the details, we just skipped it. We said that you can refer to the paper and the thesis, but let me just take you through at least a few of the questions which was posed to these drivers. We said that there were 7 drivers who were asked, and one of the key things in this is also the correlation of the answers to the drivers. There are 2 things in this. One is the correlation of the answers to the drivers and the correlation of the questions itself. The questions require similar response from the driver, and whether these questions were similarly responded. So this is also important. We also said that the experimental car which Dr. Chen and Ash used at the Leeds University, they had 8 vehicle parameters, okay, and then these 8 vehicle parameters were changed and 16 configurations were arrived at, or 16 different cars were the ones which were tested. Of course, Adams' model has been used as well in order to get the objective rating, and experiments were conducted in order to obtain these ratings as well. Okay, so let us now look at what are the type of questions, and I'm going to just read it out so that you understand. So the type of experiments, there are 2 things. One is a number of experiments were done. For example, steady state turning or steady state cornering is an experiment that was done, okay, in a smooth road as well as in a rough road. Okay, so you have that steady state turning which were run in a rough road and in a smooth road. Okay, so there were a set of questions that were asked, and in order to determine the cornering behavior. So, for example, the question is something like this: over smooth roads, progressive behavior with increasing lateral acceleration. How does this vehicle behave when you increase the lateral acceleration? Obviously, when you say increasing the lateral acceleration, you mean that the speed. Okay, the 2 speeds which were chosen, and as the speed increases, how does this progressive behavior with lateral acceleration, how does the driver feel on that? The other thing is that over smooth roads, ease with which this line is held. Is it very easy for him to take this turn, hold the line, in other words, hold the path, or is it that he had to make constant changes in his, the way he drives and so on? Then other thing is that what is the amount of body roll or degrees of body roll, okay, which the driver feels? Third one. 4th question is that progressive behavior with decreasing lateral acceleration. Okay, so the progressive behavior of increasing as well as decreasing lateral acceleration. Okay, and an indication of the feel of available grip. Okay, and so on. In other words, these are the type of questions that were asked, and that these were rated, as I said before, in a 1 to 7 scale of rating. Okay, if you go and look at this paper, SAE paper, you see the spread of answers. In other words, it's not that every driver is going to agree, okay, on that marks. Okay, there are spreads, and it was found that a few of them, okay, it is the spread of the answers, or in other words, if you take an average as well as the spread of this, you would see for some of them it was small and some of them it was large and so on. In other words, it was not very easy for drivers to agree, exactly on every question on these things. Okay, so that's why a very detailed statistical analysis was done. In fact, in order to extract information, things like neural network was done and so on. So the first thing is steady state turning, and the other, as I had said, is, this involved totally about 14 questions. So this involved about 14 questions. Then we had this power change, as I said, on or off. We had already said that power change is going to look at the understeer and the oversteer characteristics of the car and figure out, it's an exercise, when there is a power on, would there be more understeer characteristics, or power off, would it be less, or vice versa. I leave it to you to think about it, basically because this involves what? Load transfer, okay, and when load transfer happens, what really, whether it's going to be understeer or oversteer. I would like you to think about this. Okay, so this power change involves, I think 15 to 20, that is, so 6 questions. Then sudden braking in a turn. Okay, so what happens to, for example, during this case, what happens to your response? What is the roll stability? What is the wheel lift, and so on. So these were the questions which were asked when sudden braking in a turn. Okay, transient cornering. Okay, again, there were a number of questions on transient cornering. So the third one, sudden braking in a turn, it went from sudden braking in a turn went from 21 to 24. Okay. So then transient cornering, straight line, directional stability, and so on. In other words, a total number of questions that were asked was 49. Was 49. So it's very large number of questions were asked. Now it was not that all these questions were relevant, okay, when compared to handling and when compared to subjective objective evaluation. That's why later, out of these 49 questions, a few of them became important. So the first thing is questionnaire was set, these things. This we had already seen. Okay, so out of these questions, a few of the, yes.
The purpose of doing these tests, there are two purposes to this. One is to quantify how good your vehicle is from a pure technical viewpoint, and the other is what exactly the user wants. But in that case too, why can't you just subject the user to conditions they would normally face? Why do you want to put them through tests like this?
I don't know, the user band may be so high.
No, but it makes more sense to test them in the scenarios in which they would normally be operating, and you could even use a steering robot or whatever to quantify how the performance is.
Okay. Two things. One is that if the vehicle performance at the limit is good, because most accidents, if you see, it is at the limits. If its limit is good, then handling characteristics of the vehicle is supposed to be good. Okay. More importantly, steering robo, okay, is today used for getting input for the objective metrics. Okay. Now here, what are we trying to do? One of the important key things, which in my experience we have done a lot of work, we have seen that when it comes to handling, the drivers are very sensitive. Okay, very sensitive to changes that take place. All right. That is the reason why, for example, when you have that pressure of driving, as you for example, accelerate in a corner, okay, and the vehicle feels that acceleration in a corner, okay, gives you a sort of a good feeling of the car. So in other words, the feeling as you drive the car is brought out by this subjective evaluation. Right. Now, why are we, okay, let's put it like this. I have objective ratings, okay, objective parameters, okay. First of all, I do not know, suppose you remove the subjective drivers. First of all, I do not know what can be this list. What should be this list? Look at the list. You know, there's so many things which we had seen yesterday. So what can be this list in order that I would satisfy a good behavior of the vehicle? Okay, I don't even know it. So that is why I want a subjective to objective correlation. Okay, and the car is tested at its limit because I do not know, how it will be used. Right? I mean, we are not talking about cars being used only at, say, in our roads where you can't go beyond 40, or in any city road where you can't go beyond 40 kilometers per hour. We are not testing cars just like that. Okay? They are tested for different purposes. For example, there is a city cycle. The city cycle is used in order to find out what is the fuel consumption. Okay? For example, our roads, we test the cars for very sharp transient maneuverabilities. Okay? So which is also reflected here. So in other words, the city cycle, it has its own use to evaluate the car, especially from a fuel consumption point of view. But when you want to look at the performance of the car, say, suppose you take this in a highway, okay, and we know in our highway suddenly there is an obstacle that comes, okay, and you do a double lane change under very severe conditions. You're traveling at 120 kilometers. I don't know whether you have driven these highways. In Indian highways today, people drive at 140 kilometers to 160 kilometers per hour. We know that some of the buses, for example, we have done a lot of survey on tire lives. We know that buses average 105 kilometers per hour. Okay, so these speeds are extremely high, extremely high. So at those speeds, okay, we do not know how the vehicle is going to behave. There have been issues when the vehicle touches 110 kilometers per hour. Okay? There are countries in which there are restrictions on speeds, for example, United States. Okay? In our country, we do not have, most instances, we do not have restrictions on the speeds. Okay? In many countries like Germany, you do not have restrictions on speeds. So you do not know at what speeds people are going to drive. So that is why all these things are tested. Simple fact is that the drivers also do not want surprises. Okay, when you do a transient understeer or transient oversteer, the drivers also do not want surprises. So that's why we do such a subjective rating. So once I do a subjective and I do a subjective objective correlation, also my design becomes simple. Now if I tell you that my yaw rate gain at 0.7 hertz is important, then my next goal, which you will do in the next course on our vehicle dynamics lab, as to what are the design parameters which are going to have an effect. We have seen this with a simple bicycle model, right? But there are other parameters which may have an effect. In a very detailed models, there are other parameters which may have an effect. So it becomes easy for me once I have that kind of range which we defined, okay, that kind of range which we define, then it becomes easy for me to also design a vehicle. Clear? That's why. So what are the important things? How do you design a questionnaire is important. Okay? What are the type of questions, relevant questions are you asking? Okay? That is why the questions where objective metrics are found to model majority of the driver ratings are given here. Okay, go back and look at the thesis by Ash. You will do more about these questions. So from these 49 questions, a few of them become important. Okay, and tomorrow you want to test a car, it's good to have or to model this or to have a questionnaire, design a questionnaire based on these questions. Okay. So it's a big topic. I don't have time to go into each one of these questions and how it is related and so on. That's why I've given you a reference. I would like to move to the next topic. Okay. But just want to spend a few minutes on what this subjective rating questions tell you. Right? Of course, ultimately when you want to buy a car, you're going to drive it. That's a different thing. But this is useful for the deciders. Okay, at least now with the vehicle dynamics course, you will also know how to test a car. Right? So that's, yes? Okay. You can do a test drive. Okay. Post that you're going to buy a car, go and do a test drive and say that I'll tell you a decision after a couple of days. Don't give your cell number to him because he'll keep calling you. Right? Don't do that. Go and do these tests. Okay. Fine. Anyway, we're going to do a few tests in the next course on vehicle dynamics lab. We'll know more about these things. Right. So we will move away from this subjective-objective correlations. We will move to a last topic in lateral dynamics, which is rollover. Yes.
When we try to correlate subjective and objective things, we took only Memuro plot, right? But it's not.
No. I told you, right? I mean, Memuro plot is the easiest because I have only 4 parameters. Okay, that seems to correlate well. To a great extent, in my opinion, we have also done some tests. It correlates well. Okay, except that when the vehicle has a lot more oversteer characteristics, then there is an anomaly. In other words, what we said is that within a limited range, the sentence that as the area of the rhombus increases, gives a better drive or handling is valid. But then this work, further work after Memuro, after all it was in early 90s. So there were a lot more parameters which were included. Okay. Now those are the parameters which we had put down some time back, right? And the difficulty as you add parameters is that I want to now be within that range. Then it becomes difficult whether I can have all those parameters within a range, within that range.
Because it varies with geometry.
That's exactly, see, that is why the subjective, how will you predict the range? There are 2 things. One is predicting the range, the other is getting the value in a design. The predicting the range is that subjective-objective correlation. That's what I've been talking. Subjective-objective correlation gives you that range. Okay? Clear? So, in other words, that's why drivers are asked to drive, look at their answers, then what are those cars which they have said very good, what are those ranges, and so on. That is why you did, or people did in the Leeds University, did a factorial experiment. Okay, so this range is obtained from that correlation. There are a number of ways in which they have obtained this correlation. Okay, so range is different from design. Then you have to go and design a car whose, for example, natural frequency is between these two, 1.7 and 2.1. Okay, so this is applicable to a range of, say, a sedan, okay, up to SUV, right? But may not be applicable for, say, trucks type of thing. Okay, so this range is for the vehicles tested, which is sort of sedan SUV type of vehicles. This range is valid. Your question is well taken. So that's why if you are working in a car company, you would like to have your own these numbers. Okay, so that you can fine tune it. So this will be very useful for you to fine tune your vehicle.
Say I want to design a car and I want to predict my range.
You can't predict the range. See, this, you can, if you, when you design a car, you will get the values for these things. You will get the values. The range is predicted, as I keep telling, between subjective objective correlation.
It's just subjective, right? We didn't ask any numbers there. It's just, it's like how the car is when you turn, things like that.
Yeah. So there, what we did was we asked to rate it as 1 to 7. Okay. In fact, that's why this paper, I don't have much time. 980226 SAE. There is a table, say figure 4 rather. Okay. Figure 4, you get effect of objective metrics on subjective ratings. It's completely given there. Okay. Go and have a look at it. For example, effect on subjective ratings is in the y-axis, and you see that a very many number of objective metrics are given in the x-axis. Okay. So when you change this parameter, say for example, natural frequency of yaw at 0.7 yaw or yaw gain at 0.7, what is the effect on subjective rating is obtained. Okay. And he had also defined whether there is a uniform agreement or the drivers have unequivocally said that this particular parameter is important and so on. Right. So that is how this is arrived at. Change it, for example, I mean in simple words, I change the configuration. So let us take one thing. I change the natural frequency. Okay, let's forget about the rest of it, just as an example. Okay. Very good statistics is involved, but let's forget it for a minute. Just to make you understand, I know that as students you will be wondering why we are doing these things. So let us forget about everything. I'll say natural frequency. I'm going to take, say, 3 cars or 4 cars, okay, whose natural frequency at yaw varies from 1.6, okay, 1.8, 2, and 2.4. Let's say that I take these cars and I give it to the drivers. Okay, and ask a number of questions which I had listed. Okay, how does it behave in a turn? Whether you are going to hold it, you know, is there are you losing a grip, or and so on and so forth. And I'm going to ask them a number of questions. Now, then, if I consistently get that drivers say that your car, which is 1.6, okay, is not good, or his ratings for the questions are low for 1.6 and becomes high for 1.8 and 2 and again low for 2.4, okay, right, then I would say that, look, this range consistently, if they say it, and there is a statistical significance, there are a number of statistical significance tests, go through this thesis, then you would see that with 95% confidence, you know, there are what is called as R squared values in statistics and so on. Forget about all that jargons. Just say that these 2 values, okay, consistently people say it is good. Then I would say that, look, if the natural frequency at yaw is between these 2, people say that it's a good car, and so you should keep it like that. Okay. Now we can't change. Okay, let's say that I change similarly damping and so on. I keep changing one by one, and I want to find out each factor. That's one way. But I can't do that because there are so many factors I can't do. So we do a factorial experiment to understand, okay, the interactions and between the driver's field and this, and arrive at a set of values. Clear? So once you arrive at it, you go and start working in your design. Okay. Now, so natural frequency of yaw, how is this going to be related? The first thing I'll do is to go to a bicycling model. You already know the formula for it. Okay. So you look at your vehicle. Where do I stand? What is my natural frequency at yaw? Okay. Simple first cut. Okay. Maybe 2 degree of freedom or 3 degree of freedom. Where do I stand? Yes. Looks like it's fine. Okay. Like that, whatever is possible for me to get, okay, yaw velocity gain or lateral acceleration gain, okay, phase and so on, all these things I have simple formula, and first I'll check. Okay, what are the parameters? Maybe the mass of the vehicle will have an effect, CG location may have an effect, moment of inertia may have an effect, lateral compliance may have an effect. So many things may have an effect on these things. Okay, then my job as designer is to optimize this and see that my vehicle lies in those ranges. That's a challenge. It's a good optimization problem, which we'll do that in the next semester. I assure you that we are going to do a complete sensitivity parametric analysis. Okay, we will take a car, we will change various parameters, we'll list down, okay, various parameters, and then you're going to change them and see how these parameters are getting affected. So you can come to a very optimized car. Okay, so in other words, if you produce this car then and give it to these ratings of the drivers who are very important, okay, then you will get good ratings from them. That's the fundamental basis. Yes.
But at some point it took someone to identify what these parameters are, right? That is probably the tougher job, because even now you're not sure if whatever these
Absolutely.
guys have done
That's a two good PhD. That's why I took that in this course. Two good PhDs. We have done a lot of work. Okay. In my opinion, it's an exhaustive work that's done. Right. That is the the two good PhDs from Leeds, and that's what they had done. But the problem is, it is not one-to-one correspondence. It is not that for that one question there is one objective parameter. It's not like that. It is, that is why the statistical base, I keep on telling that becomes important.
But like you said, whatever the Mimuro guys had done wasn't valid in a European car or something.
No.
Whatever these guys have done might not be valid in our setting.
Yeah, correct. If you are in that, I would say, range, okay, this will be valid. That's why I said that mostly if it is a sedan, okay, or SUV, this would be valid. Okay, so yes, the validity has to be checked. We're not questioning that. But generally, because of the range that was done, okay, this likely to be valid. Okay, this is not something as a design rule we are saying. That's why we are giving a range. Around this value looks correct, looks valid.
Even more than the value, the metrics themselves. How can we be sure that?
Yeah, correct. So that is where again I want you to go through the thesis. We will do that, next semester in another course. Okay, we'll go into details. So we are only scratching the surface. In this whole course, we are only scratching the surface. Vehicle dynamics is a huge topic. Okay, the questions which are still not answered is, I said that there have been some answers. I'm not convinced that every metric has been answered from a very, I would say, use again the word, from a very objective fashion. In other words, some of them you may know that the response of the vehicle is in that frequency range, and so the phase becomes important and so on. But for some of them, you don't even know. So for example, why is it at 0.4, 0.6? If you go back and look at it, the list of, for example, metrics which they have studied, okay, which is given in their table 2 in this paper. So you would see that the metric is studied at, say for example, 2 and 4 meters per second, plus or minus 2 and 4 meters per second, and that the peak lateral acceleration response time is taken at 2 and 6 meters per second squared lateral acceleration, and so on. Okay, so in fact, the authors themselves agree that this kind of, why is it, I wrote down a formula. Why is it that it is 1.1 multiplied by something minus 0.5 multiplied by something plus, that's still not clear, right? So that is why it is purely two data sets connected by statistics. Okay, this is just a parameter identification. Okay, some have meaning, some do not have meaning. Okay, I do not know why it is 1.1. Say if you look at, say, I mean, just like that, I've given a formula. I don't know why it is minus 1.1 into yaw rate gain at 0.4 hertz. I don't know. That's what the statistics throws out. at you. The regression analysis throws out, again, that's the value. If you ask me why 0.7, just a statistical output. That's all I know. I don't know more than that. Why minus 0.7 into this? I don't know more than that. Okay? So, in other words, subjective objective evaluation is still in the realm of statistics. Okay, it's still in the realm of statistics. You are correlating it through statistical means. Clear? Okay. It's a challenge to produce a good car, and you learn. Okay, that's why many of these car companies have a huge data bank. Okay, so let's shift to the next topic. I know this is an interesting topic because it actually impacts design of the vehicle itself. As I said, vehicle dynamics, we're scratching the surface. It's a huge topic, extremely interesting. I know that there's so much of interest with the students. It's an extremely interesting topic. We can't complete all the things. Maybe you need a couple of more courses on advanced vehicle dynamics. In fact, I'm guilty of not covering many things connected with vehicle dynamics. For example, a lot more vibration aspects. And we are not covering the effect of suspension, steering, and so on. There's no time because of the limited about 35 hours of lecture. Let's at least get a view of, because it's an introductory course, get a view of what happens. Okay, let's get to the next topic, which is rollover, before we follow or we go to vertical dynamics. We've still a lot more to cover on vehicle dynamics as far as the vertical dynamics is concerned, and so we'll go to rollover. Rollover is a very important topic, okay, starting from SUV onwards. You would have seen a lot of accidents in SUVs, sports utility vehicles, okay, where the vehicle has, would have rolled over on the sides, one, and you would have seen huge trucks, okay, tractor trailers are some of them, okay, their rollovers, you would have seen it a number of times. You will be surprised to know that recent statistics shows that in the United States, 15,000 vehicles roll over a year. Okay, there's a lot of them. Okay, in our country, we have had cases where there are a number of rollovers. In fact, we had looked at some of the cases where there are rollovers of huge trucks which take cars, okay, which are manufactured, say, around Chennai. They are huge vehicles which take the cars, right? And usually the loss is upward of 5 million rupees, okay, because of the cars that are involved. Unfortunately, in this country, we still do not have a law on how this kind of tractor trailers are designed. In fact, what is the height and what simple ratio, which we'll see in a minute. These ratios are not followed, and so on. Okay, so there's a lot of scope to work on rollover, and in recent times, control strategies have been used for rollover prevention. As I said, again, we won't have time to go into the control strategies for rollover prevention, but let's quickly understand what we mean by rollover. The simplest analysis is what I would call as a steady state analysis, where we consider the vehicle to be rigid, okay, and sitting, say, for example, very approximate diagram, and let's say that that's the center of gravity location. Sorry, let's say that that's the center of gravity location. Let's say that these are the centripetal forces that are required, okay, in order that the vehicle takes a turn, right? And that is the corresponding D'Alembert's force, okay, or the centrifugal force, okay, which is mv squared by r, or I would call that as m into ay. Okay. Now, of course, there are reactions at the front and the rear, Okay, and that we call that as the track width. Let's say that that is the track width, which I would call as TW. Okay, and of course the weight W acts there. Obviously, you see the roll, as the vehicle takes a turn. Let's say that this is the outer tire, and that is the inner tire. Just call that as outer tire and inner tire. And the FZ that's acting here is F is at outer and F is at inner. Let us define, I'm defining it. Let's define that vehicle rolls over, or we say that vehicle has rolled over once this F is at inner. How is it going to roll over? I'm going to take, now what am I doing? I'm going to take a turn to the right. And I'm taking the turn to the right. Okay? Where will it turn over? Which side? To the left. Right? So I assume that the rollover condition is achieved when I lose contact of the inner tire with the road. Okay? This is the condition which I am assuming. Right? So let's just calculate what should be the critical AY in order that this is, this lift of the inner tire takes place. Let me call that distance as H. Okay. Now, take moments about this outer tire, okay, and tell me what should be this AY. M into AY into H minus W, which is M into G into TW by 2 is equal to 0. We talk about steady state, we are not introducing the time derivatives. Okay. No, yeah, this F is at inner, that's what I told you, no? So this is not, there's nothing here, there. Okay? So AY is equal to G into TW by 2H. It's a very famous ratio. T by 2H ratio as it is called. Or AY by G, usually expressed as the simplest formula, okay, is equal to T by 2H. The first thing that our commercial vehicle guys who carry those lovely cars have to do is to check what is their T by 2H ratios. You would be surprised, we have done this calculation, you would be surprised to know that this is 0.22, 0.23 G. In other words, T by 2H is about 0.22, 0.23, very, very low. So that's the level at which, okay, lateral acceleration levels at which this will roll over. A typical car would be about 0.7, 0.8, and if you look at Formula 1 cars, it will be more than 1.5. Very high. Okay? So the very first equation that you look at is what is called as the T by 2H ratio. There are two things that we left here. There are a number of factors, which would now change T and H. What is the assumption that we have made? We have assumed that this whole thing is rigid. Not true. Actually, the vehicle, the body, what is called as the sprung mass, is actually going to roll. Right? There is a roll center, we have seen that, and the vehicle is going to roll. So as it rolls, say in other words, as it rolls, okay, about the roll center, so center of gravity location is going to change. So one is that H is going to be affected by the roll and hence due to the suspension and so on. Okay. The other factor, and the roll is also, this is one of them, the roll is also due to the stiffness of the tire. The tire stiffness is also going to have an effect. Okay. In other words, you can imagine that Fz in the inner is going to go to 0. Okay, the whole of F, the Fz, that is the normal force, will be transferred to this tire.
Because of the suspension roll, even T should be affected.
Yes, sir, I'm coming to it. We will do one by one. Okay, so both of them are going to be affected. Okay, there are a number of factors which are going to affect both, right? Agreed. Wait. I know I'm very happy that you're so involved, but we have to go step by step, right? Okay. Yes. So that's also the roll also is affected. There are two rolls here. One is the roll of the unsprung mass, which is basically due to the tire stiffness, because of which there will be let's look at the suspension system or this axle system, okay, which is a rigid axle system, which is there in most of the commercial vehicles. So because of this is going to be affected. And the second one is that because of on top of it is going to sit this sprung mass, okay, and that sprung mass is now affected by the roll stiffness. So in other words, there are factors which affect this. There are factors which affect T. Okay, there are factors which affect T. T is affected by the kinematics and compliance of the suspension system. For example, it is affected straight away, even without going into the details of kinematic and compliance system, is affected by the tire lateral stiffness. Okay, straight away, tire lateral stiffness. It's affected by the camber. It's affected by the camber change. Okay, how does this camber change, and so on. It's even affected by the torque that is produced due to the gyroscopic effects. So a number of factors affect this and this, which we'll list down in the next class. Okay, and so usually, if you design a vehicle, it is if this factor is T by 2h is equal to say 0.8. Okay, this factor usually is the actual factor is less by about 25%. Okay, a number of these things are going to have an effect. It's going to be less by about 25%. So there are at least 4 factors which have an effect. The major effect, maybe even 25, 30%, and so on. The major effect is because of this roll. Because of this roll. So my first job here, right now, is to find out what is this roll and how that affects this hedge. So let me consider 2 of this roll. Roll simply means that there's going to be an angle. Okay, 2 of them. One I would call as alpha 1. We're going to follow for this derivation. The reference is that Road Vehicle Dynamics by George Rill. Road Vehicle Dynamics, which is very simple derivation, which takes into account this. And if you want slightly more detailed, I'll give you one more reference. Again, due to okay, which I'll maybe next class I'll give you that reference. I don't have it right now. So these are the couple of references which talks about this. But one of the things which we have not done here is that we have not considered actually the dynamic effects. In other words, I have to write down a differential equation based on phi double dot, I phi double dot, and so on. That we have not done. that's the next step. The more interesting part is, okay, let's just finish this. I'll come to this. Okay, one is alpha 1, the role of the unsprung mass, and alpha 2, which is the role due to the sprung mass. Okay, we'll do this to, we'll do the detailed derivation in the next class and finish this topic. I just want to tell you that what we are doing is actually not dynamics. Even when I include these two, we are not doing dynamics. Okay, so we have to do dynamics. In other words, we have to understand the dynamic behavior in roll, and that becomes very important in order to design, okay, control systems for preventing roll. Okay, there have been a number of papers and theses on how to write down these equations. In fact, goes back to the 50s. Write down these equations, and then the recent attempt has been to rewrite the equations in state space and use a number of standard controls strategies. Okay, so we will talk about alpha 1, alpha 2 and its effect on this parameter in the next class. Right? Okay. So any questions? We'll stop and we'll continue in the next class.